previously we were looking at the amplitude shift keying, wherein the changes in the message signal are transformed over to the changes in the amplitude of the carrier, but it is done on the digital side. Okay, so it is called as a shift keying technique. Right? So we looked at the modulation technique, then we looked at the power spectral density and demodulation techniques, as well as the probability of error of the ASK signals. All right, so the next one, we'll go to the PSK. Okay? So phase shift keying, wherein the technique will be called as binary coherent binary PSK, phase shift key. Right. As the basic concept of phase modulation, it says that you have to change the phase of your signal according to the changes in the message signal. Right. So here, since it is coherent and binary, the binary says that message signal will contain on only zeros or ones. So I don't need n number of phases here. I need only two phases, right? Yes. So that's the first difference between the uh, analog modulation and the digital modulation, right? In digital, how many symbols you have, so many phases you will require. Okay. So now I have only two phases. As phases are required are two, right? It's just because the binary sequence contains only zeros and ones. Okay. So in binary PSK, we assume that we want to generate two different signals to represent binary 1 and binary 0. Okay, right. So let us assume that let S1 of t, I have to generate two signals. The first signal is 2 times EB by TB under root. It's a cos function. All right, this is cos of 2 pi f ct. So this is 0 less than or equal to t less than or equal to tb. This is the first sequence corresponding to symbol 1. All right, and we have the second symbol. So this is S2 of t. S2 of t is root of 2eb by tb. We'll write a cos itself. Its cosine value of 2 pi fct plus pi. So you see, we are adding a phase of pi radians to the previous symbol to get the second symbol. This also will exist only between 0 less than t less than or equal to tb. Yeah, correct. So first signal plus a phase of pi radians gives you the second signal. Okay, so that's how it is. They are differentiated. So here the TB is the symbol duration and EB is the energy per bit. All right. So here TB is the symbol duration and energy per bit. Now, always we have to take care that the carrier frequency, right, that is FC, has to be chosen in such a way that FC is always much greater than the 1 by TB symbol duration, right? It should be bigger than the symbol duration. We know that concept, right? So I'll just write FC is the carrier frequency. So the condition is that fc is much much greater than 1 by tb. All these conditions, we assume that we will satisfy them. Okay. And it's not, again, since we are going for a digital, we prefer keeping fc as some integer multiple of 1 by tb, because it has to be a harmonic by default. Okay, fine. Now our intention is that first we observe, we have to find a phi 1 and phi 2. Okay, so our basic intention is being identifying the basis functions, right? So but just before that, I have to decide whether I need one basis function or two function, because here we see our the constellation will be something, there will be 2 points. You don't, we don't see a zero here, correct? S1 is something, S2 is also some other coordinate. It is not zero, right? So previously, if you remember, in ask one of the symbol was zero itself. We were not sending anything, we were simply turning off the modulator when symbol 0 was supposed to be sent, correct? Right. So uh, now we have to identify what is the phi, right? That is a basis function, right? We will observe one thing here. S1 of t and S2 of t are basically out of phase by 180 degree signals, right? There is a 180-degree shift, in the sense you get any value. It's let's assume on the real axis. Okay. So yeah, correct, correct. So if I say a point which is uh, this is, say, S1, right? And if I say this is the 0, correct? The S2 will be on the other side, that's all. It's minus S1, correct? Because cos of 180 plus theta is minus cos theta, right? So this is cos theta, this is minus cos theta. That's the very basic idea. Anyway, we'll write the constellation diagram later. So just to decide that how many the phi values we require, or how many basis functions we require, we are using this concept now. That's all. Since there is a phase shift or phase difference of 180-degree between S1 and S2, okay, I'll write S2 equals to minus S1. From this, okay, there is a specific name for these kind of out of phase signals, specifically 180 degrees. Okay, if you, those signals which differ by 180 degrees in phase, we have a name for that. They are called as antipodal, PODAL. Okay, antipodal signals, right? But when I see the equation, it's very clear that uh, first signal is something into cos of 2 phi fct, some s2 is minus of that, correct? So whatever you use to define s1 itself can be used to define s2 with a minus sign, correct? So antipodal signals, so this implies we need one basis function. Okay, this implies single single basis function. Define that, say phi 1 of t equals to, leave the energy part. Okay, energy comes from the message, right? Without energy we have to write. So this is root of 2 by tb into cos of 2 pi fc into t. So 0 less than or equal to t less than or equal to tb. So we define a basis function like this. So this implies, let's write what is the symbol s1. Therefore, the signal you are going to send for S1 of t will be a root of EB times this phi 1 of t. 0 less than or equal to t less than or equal to tb. At the same time, S2 of t becomes equal to, it's minus of root EB into phi 1 of t. So 0 less than or equal to t less than or equal to tb. So get a phi 1, which is a basis function, and obtain S1 and S2 by using the phi 1, okay, multiplying by the energy of each of the symbol. So we try to keep this energy also uh, equal for both. Okay, so first has EB, second one has also have EB under root. Uh, Sign is changed because of the change in the phase. So now our intention is to visualize this signal, how this is going to look like in the time domain. If at all we plot, okay, let us assume we try to plot the PSK signal for, I think we wrote a similar one for ESK. For the similar symbols, we try to plot the wave, okay, right. So, okay, let us assume that we are going to send this following symbols. This is 1, 0, 0, 1, 0, 1. Okay, and let's divide the space of each symbol gets a TB equal to this much. So now, uh, so there is another duration. This is another TB, and okay, in this, so we assume a fixed frequency, right? That is FC. So with FC, we will plot, say, a waveform for, okay, let's keep the amplitude also fixed. All right, so let's say that the highest amplitude it can reach is that, anyway, the root EB will take care of that, right? So that's the highest value it's going to take. So this is, let me see, root of EB. Okay, I am going to have the same value on the other side, but that will be minus of root EB, minus root EB. Okay, between this, now we will plot the waveform. So let's assume, so this starts like this, like this. Let's assume we get two complete cycles for one. Now you see symbol changes. So symbol changes indicates that it should be negative of the uh, whatever waveform, right? So waveform is supposed to go like this. It will be the opposite of that. Instead of increasing, it will be decreasing now. So it starts from the same point but moves on the opposite side. Okay, so this is the phase shift by 180. So right, you see now there is no change in the symbol, so it will continue, right? So it's like this, and it comes like this. Now you see the change of symbol is 1 now, so it actually it moves in the opposite, right? Again there is a change, so comes down this and like this. Now you see there is a change of, okay, just a second, I have to, we'll draw two complete cycles in one time period. Okay. like this. Now this is uh, one was like this. Okay, I think I made a mistake, right? So it should be on the opposite side because sign changed, right? So it should be, yeah, yes. So it starts from here, goes down, increases, comes down, and increases, and comes down. Right now the change of phase, and it will be okay. So you can see that, right? The points where we have the where the symbols change, right, from 1 to 0 or 0 to 1, you have a change of phase, or it is considered as the phase reversal, right? I'll mark down those points where we can see the phase reversal. Okay, so this is, so these are the points of phase reversal. So we can see that whenever the symbols change from 1 to 0 or 0 to 1, we have phase reversal. So the phase reversal is a characteristic of the PSK, right? So in continuous modulation, the phase modulation was continuous in the sense phase used to change continuously throughout the waveform. So we didn't observe the abrupt changes like this. Okay, right. Whereas here, since you have only two phases possible, the change is, yeah, change is abrupt, and we can directly observe that it's going to be like this, right? 180 phase shift. Right. Now, let's go ahead and look at the PSD, right? So power spectral density is equally important, corresponding to any of the modulation, right? Because that gives you an idea that how many, okay, what is the amount of power that has been kept or allocated uh, at a particular frequency, what power, right? How the power is distributed, right? Now, the power spectral density of BPSK, first we'll write the general format. Okay, so this is what we are expecting. S of F is equal to, this equation remains same, 1 by 4 times uh, 1 by 4 times SB of F minus FC plus SB of F plus FC, right? Where SB is the baseband PSD. So first we'll identify what is a baseband PSD. Actually, there is a derivation, right, to obtain that equation. For the time being, let's write it directly. Okay, so the SB of F is given by A square TB into sinc square F times TB. Okay, so this is the PSD, and it indicates that we have a sinc function coming in picture. That is because of the rectangular, the box like structure, right? So actually the whole, yeah, so you have a fixed, it's like a rectangular shape throughout. Inside the rectangular shape, you have a cosine function, right? So the rectangular nature dominates. So I don't see a delta function coming into picture, right? Like ASK had plus something into delta function, right? That is not there here. That's a basic difference between the phase modulation and the amplitude versions of the same, right? Now, uh, okay, we got this. Let's that first plot this. All right. So the plot of the um, this is the frequency axis, and this is the S of F. Right. This A square TB into sync square function is there, right? This is going to be shifted to the right by FC. Also, this is going to be shifted to left by FC. Right and left, you shift by FC amount. That's that's how we get the required waveform. So at the center, let us assume that this is corresponding to FC. On the other side, you have a value minus FC. Now let's assume a peak value. This is the peak value. This is corresponding to, let's say, a square by 4 into TB. That's the highest value. So corresponding to that, I have a point over here. From there, the waveform begins. We'll assume that this comes down, goes up, and comes down, goes up, and so on. Similarly, even on the other side, I have to comes down, goes up, and so on. So here the characteristic of this particular waveform is that the main lobe, which is written like this, has a gap of 2 by TV. This is the very basic characteristic related to the PSK itself. All right. So the same thing we'll write on the other side as well. Let me write the equation. This is a square by 4 times TB into, see, this is the sink square of F minus FC. This is the right shift. Okay. F minus FC into TB. That's the right shifted waveform. So also it has a characteristic that it's going to touch the zero line for the second time at FC plus 2 by TB. So first one will be FC plus 1 by TB, and we will not write that. It's understood like the previous case. This is FC minus 2 by TB, the second point. Okay. Second time, it's first time it's going to, anyway, we have marked something else. That's why I'm not writing it. Right. Okay, so same thing repeats on the other side. So it begins from there, comes down, goes up, and comes down, and dot. Same thing will be repeated. Okay, so this point is minus FC plus 2 by TB minus FC minus 2 by TB. This also has the similar lobe width, and that is equal to 2 by 2 by T. And we can write the equation for this the left hand side waveform as well. So that is a square by 4 times TB into sink square. Since it is left shifted, it becomes F plus FC times TB. So here now we'll write what is the A square, right, or A. So where A is equal to, previously we had written that it's actually the amplitude factor, right? Amplitude that is corresponding to this. So that is given by, it's actually the product of your root EB, which is the amplitude of the rectangular pulse, and the carrier amplitude. Amplitude is root of 2 by TB. So first let me write how you get this. This is root EB is the amplitude of the message into the carrier amplitude, that is 2 by TB. So we can write this is root of 2 times EB by TB. Right. Now I have a question that when we see the power spectral density, I can understand that most of the power is allocated around FC, right? And I have a little bit of energy or the power that is getting distributed for the side lobes as well. But our intention is that I want, if you want to pick up the signal on the other side, that is on the demodulator side or the receiver side, before you demodulate, you may mostly we will uh, design the antenna to pick up this part of the signal, correct? Okay. Now, which means we are not bothered about these side lobes, correct? We are actually concentrating exactly on this main lobe of this, right? Now, which indicates that if at all it is possible, if at all it is possible to uh, to put more power, to remove the power from side lobes and to increase this further, maybe if you can increase this like this, it's good for us, right? Because you are actually removing the power from the side lobes and you are going to put that onto the main lobe, which helps you in that signal detection, right? What are the parameters that we can change, right? Because it's under the control of the modulator may have some authority to increase the main lobe, right, and reduce the side lobe. What parameters of the modulator, right, or on the modulation side you do some, anyway we have many variables over here. What are the variables which we can try to change or try to increase or try to decrease so that this main lobe increases further, right? Main lobe increases, what we are expecting is we may try to reduce this. We want to concentrate exactly on the center, right? Or you want to put the, maybe my intention is to make a lobe like this, possible, right? In such case, see, the width is defined by 2 by TB. Will tend to, okay, at the same time, that's the right answer. I will try to increase the TB, right, in my signal, right? Instead of fixing this as the TB, maybe the TB could be somewhat like this, new TB value. It's a bigger TB, right? So that we understand the frequency side is 1 by TB, right? Frequency will be decided by 1 by TB. So it's going to be a sharper frequency, correct? Okay, that's fine. But we have another problem over here. You see, the amplitude is also decided by TB itself, right? As you increase the right TB, it will increase, right? So that is actually right. It's actually a good thing for you, right? As you increase the TB, this is going to increase. So my intention was to come closer to FC, and my intention is also to increase this. Both you can achieve by varying the TB itself, right? Again, there is another factor of root EB coming into picture, right? That's good for you, right? You increase the energy per bit, that is also going to increase, right? Using the, yes. So you increase the EB value, energy per bit of per symbol, right? Energy of each symbol. If you increase, that is also going to help us in achieving what is required. right? So that's what we understand by looking at the waveform. So this is the usage of what you call as the power spectral density, what frequency, what power you get using this. This is one of the basic feature which we use even when we design the receivers, okay, demodulators, etc. What exactly, exact frequency you are supposed to look when you receive something, right? Because for each and every frequency we can design the demodulators or the receivers. All right, moving on now. Yes, sure, please. Based on the hardware limit we have, right? Some optimum TB has to be selected. Not very large, not very small. Now, whenever we are going to represent this signal uh, in in terms of the constellation diagram, how to identify where is the point? Anyway, we understood that it is EB and minus EB now, root EB and minus root EB. Correct. But we need a mathematical proof for that, right? How to obtain that? By using the orthogonality concept in one-dimensional space for a binary PSK. Uh, Basically using the antipodal signals, we can represent the coordinates of the point using the following equation. This is the general equation used in any of the modulation techniques to obtain the points in the coordinate axis. Okay, so that is like this, right? The coordinates of message points you can obtain by using, so let me write S11. This is the general equation, integral 0 to the symbol duration. Take the first signal, that is S1 of t, into phi 1 of t. Phi 1 is, there is only one here, okay, tt. So since both are 1 1, we could give a notation like S1, okay, indicates that first signal into first phi. Okay, so this actually we can do the integration. I'll skip the integration part, solving the integral. It comes to be root EB. Then S21 is equal to integral 0 to TB. Now use S2 of t into phi 1. So this comes to be minus of root of EB. Now let's plot. This is the constellation diagram. For plotting the constellation diagram, point S1 is over here and say S2 is there. So the phi 1 is my axis and this is the decision boundary. Decision boundary that corresponds to 0, right? So S1 has a value, that is phi 1 equal to root EV. S2 has a value, the phi 1 becoming equal to minus of root EV. And this region is, this is region 1 and this is the other region. So let's give some name. Region Z1, region Z2. Z1 is corresponding to the first symbol and Z2 corresponds to the decision Whenever a point falls in this region, it will be assigned to S2. It will be detected as second symbol, that is corresponding to 0 by the receiver. Now, we'll go for the modulator and the demodulator structure. So, the input signal consists of ones and zeros. Again, we are assuming that to be the binary wave. We can simply write it as binary wave. Basically, it consists of zeros and ones, but what we write is in terms of the energy. So either you have plus root EB or minus of root EB. This is coming from one side. This gets multiplied with a product inside a product modulator. This is going to get multiplied with our phi 1, that is equal to root of 2 by TB times cos 2 pi FCT. Right? So this generates the binary PSK, that is S of t PSK signal. Right? The modulator is simple in terms of the block diagram when we write it. Next, we'll write the demodulator. Let us assume that from the antenna we pick up the signal, and this is maybe the S of t, out of which something is picked up by the antenna. Let us denote that as X of t. As this technique is uh, the coherent detection. Coherent indicates that the receiver, in terms of the frequency, yes, it knows what is the phi 1 basically. It multiplies with the phi 1 of t directly with the receiver signal. Okay, and whatever is obtained over there as a result of the product, it performs an integration 0 to t, that product into dt. So it knows the value, so it will perform this, and the in the next step okay, then once we have the result of this integration, in the next step it's going to perform the sampling. All right, so we have the sampler over here denoted by this. So this is going to touch this every TB. Okay, sample at every TB. So it will perform the sampling operation like this. And once the value is obtained for a given sample. Let's denote it as x1. All right. Now, like we have in a standard decision making circuit, there will be a part of circuit that takes up the decision. In order to make a decision, what do you expect? You need the threshold value. Threshold. So we know that the threshold is in terms of a voltage here. So you can make it zero, because on the concentration diagram we have seen that the central decision boundary is at zero. Now, dependent on the x1 value, after comparing it with the threshold, right, we get a binary wave. So its value will be like this: binary wave. This is equal to 1 provided the x1 is greater than or equal to 0. It is going to be 0 if x1 less than 0. So you see, the output is either 0 or 1, depending on what is the value of x1 we get, right? And it's after being compared with the threshold. Then we'll move on to the last topic of the PSK, that is the error rate, probability of error. So probability of error in this case can be derived and prove that this is equal to half of the error function root of EV by N naught. So in ASK, the difference is that you can see a half over here, right? Inside the bracket you have half. Now that is not there. Okay, so this is the equation that we can derive to get the probability of error. So what is the chance that you send 1 and you receive a 0, or what is the chance that you receive a 0 on the other side when 1 is sent? Right? So this can be calculated and prove that this is equal to this, and it's very clear that it depends upon the EB and N naught values. Okay, it simply depends upon what is the energy of your bit and what is the N naught by 2 that is present in the given communication channel. So here we assume the Gaussian, right? Gaussian noise, and it can be varied. Okay, it can be changed depending upon what type of channel you are using and what is the amount of energy of the signal that we are sending over there.